Hello everybody, my name is Alex, and today I want to talk about how computers actually work at their lowest level. And I want to expand on it a little bit, and I'll just tell you something hand-wavy like CPUs are the brains of your computer, or something similar. I think most people already know that. What I want to focus on instead is to explain what CPU is actually doing and what RAM is really storing. So the core of what makes a computer is just two things really. It's its memory and the CPU. And by memory, I mean RAM. You can think of any other peripheral device that connects to a computer as having one of the two purposes. It's getting things into RAM or taking it out. Think about RAM as a gigantic sequence of cells storing numbers. Let me draw it. For the purpose of this explanation, I'll take each cell equal to 1 byte. And I don't want to go too deep into details of a binary systems and zeros and ones, but you can think of a byte simply as an amount of memory required to store any number between 0 and 255. The sequence of these cells inside RAM is numbered, and the number of each cell is what is called a memory address. And before I go further, I wanted to stress once more some important points here. Your entire RAM is just numbers. It's not an abstraction or some simplified analogy for the explanation. It's literally what is inside your computer. Theoretically, you may take your RAM out and write it down as a sequence of such numbers by hand. Only such sequence would take a lot of paper and space. For example, a typical for modern day computers, 8 gigabytes of RAM, would require 8 billion 1-byte cells. And if you write this in a sequence like I did on a piece of paper, you'd have a line of 40,000 kilometers long, or 24,000 miles. It's enough to wrap Earth around the equator, so that's a lot of numbers. But they are literally just that, numbers, one after another, from 0 to 255. Well, you may be thinking right now, gee, can it really be just that? What about sounds, pictures, games, or applications? These things surely must require something more sophisticated. Can it really be just a lot of integers in a range from 0 to 255? Well, it can. The secret that makes them pictures and sounds in computer programs is interpretation. So what do I mean by that? Let's look at a simple example. Let's say you have a fitness wristband and it has a tiny black and white screen of incredibly low resolution, 5 by 4 pixels. And when the band measures your heart rate, it may render this nice little heart on its screen. So how exactly does it do it? Well, we already know that this picture must reside in the RAM. And the way it's encoded is actually very simple. The display on your wristband just knows that within certain memory range, each memory cell represents a color of a pixel. For example, it may know that it can read memory cells starting from number 100 to number 120, one by one, and if it sees 1, the pixel will be black, and if it sees 0, the pixel will be white. As I promised you, it's really, really simple. And it doesn't only work for a tiny wristband, it's pretty much any computer screen, Full HD or 4K, or your smartphone that is built this way. This chunk of memory representing pixels actually has a name, and it's called a frame buffer. And for modern computers, you're probably going to need much more memory cells than in our example. For instance, 4K monitors would have 8 million pixels, and because these pixels have color, they would require 3 memory cells per pixel for red, green, and blue color channels. You would need 24 million cells to store all of it. And I just want to stress it again. The RAM itself doesn't really know nor care that bytes inside one cell are images and the other ones are sounds or anything else. The data itself doesn't mean anything unless some peripheral device knows how to interpret it and use it to convey the information it encodes. If something goes wrong and the monitor tries to render wrong cells of memory, or something on your computer tries to write into the frame buffer, you'll see glitches because your monitor will try to paint pixels with bytes from memory cells that aren't meant to be a picture. For example, let's take a look at this glitchy laptop. You can see here that it seems like the monitor tries to render something that is not meant to represent pixel colors. The fact that there are some patterns, like here and here, supports this theory that it may have happened because there was some error in software that led to writing non-image kind of data into the frame buffer. Okay, now back to the CPU. How does it work and what is its role in all that? Well, CPU is pretty much the only thing that can modify data in your memory. How does it do it? Just like a monitor looks at a memory chunk and quote-unquote sees a picture, a CPU interprets a range of memory as a series of simple instructions for itself, the instructions that tell it how to modify the data in the RAM. Let's look at it closer. The CPU itself has a few memory cells that are called registers. Unlike billions of memory cells in RAM, there are only a handful of registers in the CPU. For example, on x86 architecture, the classical Intel CPUs, there are only 8 general-purpose registers. In ARM CPUs, there are 16. So you may ask, why does CPU need them at all? Well, the reason is because CPUs can't modify the data in the RAM directly. What they do instead is copying a cell from RAM into the register, performing an operation in it, and then copying the result back to RAM. How does CPU know where to look for instructions? There is one special register in the CPU. It holds a memory address, which is just a number of a cell, that contains next instruction to execute. On x86 architecture, this register is called EIP, or Extended Instruction Pointer. So what kind of instructions CPUs can run? As you may have already guessed, nothing really sophisticated. The brains of your computer are actually not very smart. They're just really, really fast. Okay, let's look at an example. Let's say we want to do a really simple thing. We want to fill all memory cells in a certain range with number 0. I'll explain the usefulness of this quote-unquote application later. The algorithm might look something like this. Step 1, set register A to 0. This register will hold the number that we will fill the rest of the memory with. Step 2, set register B to the start address of the memory range we want to fill. In our example, it's going to be a cell number 5. And everything starting from this cell onwards will be filled with whatever is stored in register A. Step 3, copy register A, the one with the target number, to the memory location that is stored in register B. Step 4, add 1 to register B. Step 5, go back to step 3. Okay, so you may be wondering now, like, why should we do it this way? Why can't we just tell CPUs, fill in zeros from here to here, and that would be just one step? Well, the reason for this is that CPUs can only work with one number at a time, and they can only do calculations on their registers, not values in the RAM itself. You may also ask, why is it like that? The full answer could easily take a video 3 times longer than this one, so here's the short version. It's just easier to make fast CPUs that can do simple operations like the one we described here. Okay, so CPUs can't understand handwriting at this level. How do we encode this algorithm so CPU can understand it? So here we've got a chunk of RAM that will keep our instructions. And the first step is to copy 0 into register A. Let's say the code for this command is 10. No good reason, I just like number 10. So when CPU sees 10, it just means take the number that is common in the next cell and place it into register A. When CPU is done executing this operation, it will automatically add 2 to the instruction address register that it will use to look up the next command. Why 2? Because it's hardwired to do so in its silicon in the factory. It knows that instruction 10 comes in pair with a number, so you should look for the next step 2 cells ahead. Okay, so the next step is to set register B to number 5, which is our start address. It's the same principle. Let's say the code for this operation is 20. So 20 goes here, and it means move the next number in the RAM to register B. Step 3 can be encoded as 30. It means take whatever is in A and copy into the address that is stored in B. Done. Step 4 is an arithmetic operation, and it just increments B. By increment, I mean it adds 1 to B. Let's say the code for this operation is 40. After this step, register B equals to 6 in our example. So step 5 is an instruction that modifies the command address in the CPU that is executing next. Let's put code 50 on it. And the cell right after this command will hold the address of the memory the CPU should jump to. So if we say these are our addresses and we want to go to step 3, it would be cell number 104. And so the cycle repeats. We execute step 3 and write 0 into address 6. Register B becomes 7, and 0 goes to the address number 7. And then B becomes 8, and so forth, and so forth. So the obvious problem with this algorithm is that it never stops, and it will pretty much fill the entire RAM with zeros. But it's good enough for the purpose of our explanation. Okay, so I hope I didn't lose more than half of my audience at this point. So let's summarize. What have we got after making all these laborious steps? First, as I promised, let's talk about the case when such an application might be useful. Remember our wristband with the little heart in the screen? If instead of the arbitrary cell number 5 that we used here, we used the address of the beginning of the frame buffer, we would erase the screen. So we can call our application, and make no mistake, what we did here is nothing short of a tiny application. We can call it clear screen. And that is actually a very useful action for such a simple algorithm. So second point I want to stress is yet again note that this memory range is just numbers that don't have any meaning on their own unless looked at by the CPU. Theoretically, you may try to point your monitor to this location in memory, and it might interpret this number as pixel color, but you'd probably see a garbage on the screen similar to the glitches we've seen before. And the best part is that RAM itself has no idea whatsoever what these numbers mean. They don't have any meaning outside the context they're in, and they live all together in one address space. Okay, a few more things I want to mention. Why do applications crash? One of the most common reasons for that is that you ask CPU to do something on a memory cell that is inaccessible. In our example, if I write command 30, that will try to copy register A to the address in register B, and the register B holds, let's say, 0. 0 would be an invalid address in our architecture. The application will crash. Another reason for why applications may do that is that you may ask CPU, for example, to divide by 0. What is the difference between CPU architectures? Think about CPU architecture as a different set of commands. Like in our made-up architecture, command 10 means copy constant to the register. But for Intel CPU, this code means nothing. It has its own set of rules and its own set of commands encoded in a particular way. So that's why you can't run your mobile app on your computer. The CPU on your computer will not understand numbers that CPU on your phone does. Another question you may have is how detached is our artificial example from real life? Well, the technically correct answer may be this. Very little, but there's a catch. The foundation may be simple, but every additional layer that is built on the previous one eventually leads to complexity explosion that you are more familiar from your day-to-day interactions with the computers. In a way, it's not dissimilar to chemistry. Probably explaining basics of the periodic table of elements can be real easy, but studying organic chemistry or getting good at microbiology will probably require much more effort. And the last fact that I hope will blow your mind, maybe just a little bit, all the instructions that we use today, namely copy values from RAM to register and back, addition, and control flow, they exist in real life on every architecture. And not only that, they are generally most commonly used operations in software. I found a paper online that says that 30% of all operations used in modern applications are RAM to register copying operations, 13% are addition, and 12% are control flow commands. Together they make up 62% of all code that is taken RAM when application is being executed. This includes the app or web browser you're watching this video from. 60% of it is just simple commands we made up today. Thank you for watching, and I hope you have a much better idea of what CPUs are actually doing inside your computers. There's still a lot of things I want to talk about, namely discuss actual x64, x86 architecture, the real commands, and explore real applications. But that will go into the next videos. And thanks again, and have a nice day.